Hello, my project was on cartoon classification using TensorFlow. So to first start with the challenge, right now there's a lot of really great image classifiers out there provided by the big players in tech space. Google, Amazon, Azure all do a great job of classifying photographs today. But when I uploaded cartoon images or even paintings, these are the kind of labels that you get back. So black and white, line art. If you're trying to do any kind of context analysis for media, maybe it's a comic strip, a news article, a presentation, it's probably helpful to know that this is not just a cartoon image, but it's a cartoon image of an apple to get full context. So the easy solution was to move forward with TensorFlow and create our own model. The first thing was to collect a data set. I looked for data sets online and I found one from the New Yorker that had comic strips. The challenge I saw with that was there's often a lot of other subject matter in those comic strips, so while it might be labeled something like elephant, there's a person in it, palm trees, etc. So to make it simpler, I used a plugin for Chrome called Gallerify, and it will download all the search results for any Google image search. And I randomly selected 10 different categories and then tried to make sure that all of the items in each category had at least 50 training images. That being said, because of the 10 megabyte rule for uploads, I've provided a smaller sample size in my submission to keep it under that 10 megabytes. So one thing I wanted to do was start with a baseline. Because this is a new category and I didn't know how, what was a good bar for recognizing cartoon images, I figured let's use the very best image classifiers that are available on TensorFlow first. And this is by far, this is not my submitted model, just more something that can give a sanity check. So I tested both MobileNet and Inception. These are both models that won the ImageNet challenges in the past. And Inception, I was actually really impressed. It has pretty high accuracy, which just means it's a great generalized model here with 67%. And considering all the stylization, different angles, and the relatively small data set, I thought that was a pretty strong mark to try to achieve. My final solution ended up being a much simpler model than that, and I'll go through the demo later in the presentation. But here are some of the key findings that I found. Resizing down to 64 by 64 pixels helped a lot. If I kept the images large, it ran into overfitting issues with the training set. I converted everything to grayscale, and I also mirrored images from left to right. A fish facing left or right is still a fish and doesn't lose its context. In terms of the activation function, I started with regular ReLU rectified linear units, but I actually found concatenated rectified linear units was slightly more accurate. I also started with the atom optimizer and eventually switched to the momentum optimizer after trying out a few different options with a 0.001 learning rate. I have one fully connected layer, and I actually ended up not using any convolutional layers. I tried a couple different models, one with one convolutional, another with two convolutionals, and they actually were very, very slow and were less accurate on the final test set. That being said, I know that those other models do have convolutional layers, so if I had more time on this project, I'd be really curious as to how they got that level of performance and speed by having such complex layers. So this is the TensorBoard graph of the final solution. So you can see the flattening of the image data, so it's not a matrix, the fully connected layer, using softmax to get the legit function, and then the momentum optimizer for gradient descent for the final results. And here's a quick sample of how my model did against the test set. One thing that I noticed even when I changed the random seed was that my model thinks a lot of things are fish. I have a suspicion this might be because I was able to collect more fish data, and that's causing overfitting. So that's another solve down the road, is just getting access to more data to train. So you have relatively the same sample size to train on for each category. And it was frustrating, but my final accuracy was nowhere close to the world's best ImageNet models. I got up to 32% accuracy on the test set. Obviously I was hoping to do much better than that. This is better than the early versions of the models. So some of the models I started with were 15% accurate. So I was able to optimize over time, but was never able to hit the 60% plus like I was hoping for. In terms of also what worked, the final parameters I listed in the final solution slide were the most optimal against the test set, but also something that was just really helpful that came from homework 12 for us was saving the hyperparameters. So when I change things like the learning rate, when I change the optimizer, saving that as a separate file with my TensorBoard file writer. That way I could plot these separately and really clearly see historicals on my accuracy and my loss to see how they performed. In terms of what didn't work, I touched on some of these. I was really surprised that adding convolutional layers slightly decreased the performance in the final test site, but even worse, it really slowed down my model. Because I had success improving the model by mirroring images, I also tried flipping them upside down. That decreased performance, which does make sense to me because things like a cat upside down, it changes the context. And then also, keeping the images large caused for overfitting, which I mentioned as well. This is just to show you, I flipped it to the side to fit it, but this is the more complicated model that had a couple fully connected layers and convolutional layers. The actual file, I used PyCharm as my IDE. I find this really helpful and it works really well with TensorFlow. One note was I had to add this create default HTTPS and allow it to be unverified since Mac OS didn't have the proper certificates. So this is something that you'll have to keep in mind. I break all this down in the full report. Another just kind of tricky thing that came up was PyCharm, and it sounds like other IDEs don't like dashes in the package name. So I had to install scikit image using my terminal, and I have instructions for that. And then I use this helper package that points to it and that doesn't have a dash in it. So similar to something that we've done in previous homework assignments is I set all the project parameters up front. That way I could easily adjust those and test different models. So everything from what size should the images resize down, the learning rate, the number of cycles to run the model. And then I save this as just a string that's with all the hyperparameters, and I use that later in my file writer. So that way I can see how the performance changed with different settings. Something that we didn't do in the past that I found really helpful was just the ability to preview certain images. Sometimes when I would experiment with performance and I would run into issues, it was nice to be able to preview the images and see, is there a trend across these ones that aren't doing well. When I was doing transform functions, it also helped to be able to preview if the transformations were taking place. And speaking of transformations, I have this resize and recolor image, so I will change everything to grayscale. That made everything run a lot faster, and then resize it down, which also helped performance. And then the way how this file works with this load image data function is I go to the folder that's defined. In this case, it's cartoon images. Recursively go through all of the directories and then list out all the file names. And then I use the name of the directory as the labels for that image. So if I name my directory Apple, then I'll use the Apple label for each image. Okay. The other thing that I added was, and this is using the parameter set at the top of the file, was the ability to create new images that are transformed versions of the original training set, not the test set, because I was just worried that that would cause overfitting. So what I do is I take the training set, and then in the final solution, I flip them from left to right, and that way it's just giving more variations of the data itself. And then I split everything into a training and a test set, and training and test labels. Then I initialize all the TensorFlow variables. I flatten the image data, then create a fully connected layer that uses the activation set function that's set up in the parameters. In this case, it's the concatenated rectified linear units. I define a loss function using softmax, which is pretty typical from our other assignments. I elected to use the momentum optimizer since that was more accurate. And then I calculate the number of correct predictions and then get the mean of those from the zeros and ones to get a percentage value. And then, also create cross entropy for the loss, and then accuracy for training data that I set as a scalar so I can plot it in TensorFlow. Initialize those variables, and then you'll see here that I have that file writer, and then I'm adding the hyperparameters so I can save each of the settings as different lines on our plot for scalars. And then I loop through, with a number of cycles that are set up above, get the, predicted values and the percent correct of those values, and then assign, update those, the accuracy and the cross entropy, so we can see in each loop how it's performing. And then I also found it just helpful to print every 10 iterations, 10 batches, to see, is there something just flawed. So there was a couple times where I tweaked the model, and then instantly I could see it was just all my accuracy tanked, and I just stopped my file and started over and investigated. So that was helpful rather than always switching back and forth from TensorBoard. And then I finally test against the test data, just like I did with the training data above. Calculate, the number of matches where, the predicted match to the labels, and then, calculate the final accuracy printed out. And then I also, as I mentioned before, found it really helpful to see, which kinds of images was it getting right and close. So I use that, I display all those images in a grid. So I'll run this real quick just so you can see that it's functioning. Okay, so I skipped ahead a little bit, just so you can see the batches as they're coming through here. It's funny, my model's running a little slower now that I'm doing a screen capture at the same time. At least I think that's the culprit. So you can see the accuracies as we go, and I'll skip forward until we get to the final result. Forward a little bit, it's kind of funny, it was running a lot slower as I was doing screen captures than it usually does. So you can just see it's finishing up here because I have this set to 500 cycles. So you can see my accuracy. You can see it's a lot more accurate on my training data. So this leads me to believe that it's there's an overfitting issue going on. So again, something that I would want to explore further to improve this model. And then it's slowly gonna come up with the final test set data here. So you can see final test accuracy on this run was a little over 30%. And I'll scale this down. It's not showing up on my smaller monitor, but you can see I'm predicting fish a lot. That seems solvable with the actual training data itself. But thank you so much for checking out the presentation. Please hit me up if you have any questions.